Hello, calculus fans. One of the key ideas that we studied in Calculus 1 is the fact that as you zoom into the graph of a function, you have a very hard time distinguishing that function from its tangent line. We use this to approximate functions with linear functions. What we'd like to do now is develop the same kind of idea, but in 3 dimensions. That is, for functions of 2 variables. As we zoom in towards a point on a surface, that's the graph of a differentiable function, that surface becomes indistinguishable from a plane. That will be a tangent plane. So we're extending the idea of tangent lines to tangent planes. We're then going to be able to approximate functions by linear functions of 2 variables. The graph of a linear function of 2 variables is just a plane. We can extend this idea to functions of more than 2 variables, although it's going to be harder to visualize what's going on. So let's talk about tangent planes. Let's say we have a surface S with equation z equals f of xy. And let's suppose that f has continuous first partial derivatives. And let's suppose we have a point on the surface. So P is the point x0, y0, z0. Now we discussed previously about letting C1 and C2 be curves that we get by intersecting the vertical planes y equals y0 and x equals x0 with the surface. We use this to discuss the notion of a partial derivative. So the point P that we're discussing lies on both C1 and C2. And as before, we'll let T1 and T2 be the tangent lines to the curve C1 and C2 at the point P. So we're going to say that the tangent plane to the surface at the point P is defined to be the plane that contains both tangent lines T1 and T2. Here's a picture of the tangent plane. So the yellowish looking thing is the tangent plane, and it contains both tangent lines. Now we know that the general form of an equation of a plane that passes through the point P, which has coordinates x0, y0, z0, has the form a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. And a, b, c are the components of any sort of normal vector. Let's divide both sides by c and define little a to be negative big A over c and b, little b, to be negative big B over c. The whole point of that is that we can rewrite the equation in this form. Z minus z0 equals little a times x minus x0 plus little b times y minus y0. Now we want this to represent the tangent plane at P. So if we intersect with the plane y equals y0, it has to be the tangent line T1. And if we plug in y equals y0 in the equation, then we get z minus z0 equals a times x minus x0. That's an equation of a line. And we have to recognize this as an equation of a line in point-slope form with slope a, lying in the plane y equals y0. Now, we talked about this previously, that the slope of this tangent line is the partial derivative with respect to x evaluated at x0, y0. So we know that a is equal to partial derivative with respect to x evaluated at x0, y0. And if we put in x equals x0, we'll get a similar calculation. And so the coefficient b has to be the partial derivative with respect to y at x0, y0. So here's the upshot. We get a theorem that tells us that if we have a function with continuous partial derivatives, then we can write down an equation of the tangent plane to the surface z equals f of xy at the point x naught, y naught, z naught. And this is what it looks like. Z minus z naught is equal to fx, x naught, y naught, times x minus x naught, plus fy, x naught, y naught, times y minus y naught. And let's go ahead and make a comparison between this two curves defined by functions of one variable that we saw in Calculus 1. Remember that in order to write down an equation of a tangent line, we had to do this. Y minus y naught is equal to f prime at x naught times x minus x naught. Let's look at the differences between that equation that we knew about before and this one. So the differences are, the dependent variable is z. We use partial derivatives instead of ordinary derivatives. And then now there are two terms on the right-hand side, one for each partial derivative. Otherwise, it's the same. You should see that the slope shows up here. In the same way that in the tangent plane, they showed up as partial derivatives. Those were slopes of tangent lines, and we had two different tangent lines because there were two different directions that we had to consider. Okay, that's all for now.